We're going to pick up where we left off in class for section 3.4, limits at infinity. We're going to work out these examples that we didn't have a chance to work through in class, and that will hopefully help you be able to try some problems on your own. So this first example is the limit as x approaches infinity of x squared minus 1 over x squared plus 1. The two strategies we talked about are graphical and algebraic. And one of the strategies I mentioned briefly in the video is that you can take the highest power of x you see in the problem and then divide top and bottom by that. So I'll show you what that looks like in this problem. I'll have limit as x approaches infinity of x squared minus 1 over x squared plus 1. And I'm going to multiply top and bottom by 1 over the highest power of x that I see. And the highest power of x I see is x squared, which means I'm multiplying top and bottom by 1 over x squared. When I simplify that in the next step, I'm going to get limit as x approaches infinity of 1 minus 1 over x squared all over 1 plus 1 over x squared. Now what I have here is a situation where there's a function 1 over x squared appearing in two places. We know that the limit exists of this function as x goes to infinity. That's one of the things we talked about toward the end of our class session. So we can use limit laws and the fact that we know that the limit exists of the numerator and the denominator, and we predict that the limit of the denominator won't be 0. So using limit laws, we can conclude that this limit is going to be 1 minus 0 over 1 plus 0. In other words, the limit is 1. Let's look at the next example. We have limit as x approaches infinity of another rational function, and the highest power of x we see again is x squared. So we're going to multiply top and bottom by 1 over x squared. And it's really important to make sure you multiply every term in the numerator by 1 over x squared and every term in the denominator by 1 over x squared. Once you do that, what you should get is limit as x approaches infinity of 3 minus 1 over x minus 1 over x squared over 5 plus 11 over x plus 1 over x squared. Now, we're familiar with what the limits are of these functions that still have the x in them. And we predict that the denominator will not have a limit of 0, which means we can use the quotient law for limits. And so when we take the limit as x approaches infinity, we're going to get 3 minus 0 over 5 plus 0 plus 0. In other words, we're going to get 3/5. Turns out that the answers to the questions we did in the last part of this video series for 3.4, those answers can help us determine what the horizontal asymptotes of those functions are. So let's actually answer that question explicitly for these functions. F of x is 2x cubed minus 3x squared plus 5x minus 3 over 3x cubed minus x squared plus 3. So to find the horizontal asymptotes, remember these are what we get when we let x go to infinity and when we let x go to negative infinity. We might get two different horizontal asymptotes when we let x go to positive infinity versus negative infinity. So that will be our calculus way of figuring out what's the end behavior of each of these rational functions. All right, so we start by setting up a limit. I'll do limit as x approaches infinity of this function. And again, the strategy I'm using for these functions is to figure out the highest power of x that I see and multiply by 1 over that on the top and the bottom. The highest power I see is x cubed, which means I'm going to multiply top and bottom by 1 over x cubed. And again, you want to remember to distribute the 1 over x squared to every single term in the numerator and every single term in the denominator. With that, we will get limit as x approaches infinity of 2 minus 3 over x plus 5 over x squared minus 3 over x cubed. And in the denominator, it'll be 3 minus 1 over x plus 3 over x cubed. By the fact we shared toward the end of class, if you have 1 over x to the r and you're letting x go to infinity or negative infinity, and r is a positive rational number, then this limit will equal 0. That's how we were figuring out the other limits in the previous examples. That was the fact we used that we mentioned in class. So the terms I'm circling now, these are all going to go to 0. Okay, which means our final answer will be 2 minus 0 plus 0 minus 0 over 3 minus 0 plus 0. And that just amounts to 2/3. So it turns out that one horizontal asymptote is y equals 2/3. Remember that a horizontal line is given as y equals a number. To find the next asymptote, if there is a new one, you would need to do limit as x approaches negative infinity of the same function. So if I do limit as x approaches negative infinity of 2x cubed minus 3x squared plus 5x minus 3 over 3x cubed minus x squared plus 3, well, I'm going to end up doing the same procedure, multiplying top and bottom by 1 over x cubed. And I'm going to put ... there because the calculation will end up being very similar, and we'll get y equals, we'll get that the limit is 2/3, which means we don't get a new horizontal asymptote out of it. And that's okay, that will happen a lot. What about this example? If I let x go to infinity for this function, let's see what happens. As I'm writing this down, I'm thinking about what's the highest power of x I see in the entire function. And the answer is x cubed, which means I'm going to multiply top and bottom by 1 over x cubed. Then I'm going to use the fact in red above, the fact that's right here, to try to calculate this limit, and then use that to be able to state the equation of the horizontal asymptotes. Okay, so keep going. Limit as x approaches infinity of 3 over x plus 5 over x squared minus 3 over x cubed all over 3 minus 1 over x plus 3 over x cubed. Again, you should be able to use the fact above, this one here, this one over here, to calculate the limits of each of the individual pieces. So what we end up with is 0 plus 0 minus 0 over 3 minus 0 plus 0. So our final answer is 0 for the limit, but I shouldn't box that yet because that's not what the current problem is asking. It's asking for asymptotes. Okay, so my final answer should be y equals 0. And if I do limit as x approaches negative infinity, I'll have a similar situation. So I won't get anything new for this one. And if you're skeptical about the fact that we get the same result, whether we let x go to infinity or negative infinity for this problem, we have our friend Desmos to help us out. So notice, when I zoom in, those y values, as we go to the left, look like they're pretty close to 0. And if we keep going to the left, we see that they're still making their way to 0. 0 seems to be the ceiling as we move all the way to the left. And then similarly, as we move to the right, those y values are already getting closer and closer to 0, but when we go further and further, we see they continue to approach 0.